In this tutorial, we will be discussing the simple gas laws, including Boyle's law, Charles's law, and Avogadro's law. At any given time, a gas has four definite properties: pressure, volume, temperature, and moles. And the three gas laws actually relate these properties. Boyle's law relates pressure and volume. Pressure and volume are inversely proportionate, meaning as one goes up, the other one goes down, and it's done at constant temperature. When it's actually done, it's a curved line. In other words, the more pressure it has, the smaller the volume gets. But as the pressure is added more and more, it's harder and harder and harder to shrink those particles together. What Boyle did for his experiment is he had a J-shaped tube right here, and he added mercury to it. And as the mercury was added, that volume of gas decreased. However, it took more and more pressure for that to occur. And it turned out to be a graph something like this. However, if you took the inverse of the volume, it turned into a straight line, and it became a very predictable amount. Notice in this chart that with Boyle's experiment, when you multiply the pressure and volume together of what was added and what was the result, it always came out to be the same. The pressure and volume were constant. So to sum up, the pressure of gas is inversely proportionate to that of the volume at a constant temperature and the amount of a gas. So the moles and the temperature remain the same. Although the pressure versus volume is curved, the pressure over versus the 1 over volume is a straight line. So as the pressure increases, the volume decreases at the same amount, which becomes a constant, what we saw in the last slide. That gives us this equation. P1V1 is equal to P2V2. Now let's refresh our memory. Pressure is caused by the molecules hitting the side of the container. So here are the molecules, and we actually feel the pressure when it actually collides with the sides. When you decrease the volume, the number of times that's going to hit the side is going to increase, and that's why we have an increase of pressure. So let's put this into mathematical terms and do some practice. Remember, our equation was P1V1 is equal to P2V2 for Boyle's law. A cylinder with a movable piston has a volume of 7.25 liters at 4.52 atmospheres. What's the volume in 1.21 atmospheres? So P1 V1 P2 V2. The first pressure is 4.52. The second pressure is 1.21 atmospheres. Now you might remember from earlier that there's several different units for atmospheres. For these equations, as long as they match up, as these do, you're okay. The initial volume is 7.25 liters, and we're looking for the final volume. Once again, even though we could have it in liters or milliliters, as long as those match up, we're okay. So the first pressure is 4.52 atm. The first volume is 7.25 liters. The second pressure is 1.21 atm, and we're looking for the second volume. So we're going to multiply those to be 32.77 atm dot liters. I didn't get rid of any of those units. I still have atms and I still have liters. That's why we have to make sure it's in the same unit. Times x. Now we're going to divide both sides by 1.21 atmospheres. The right-hand side cancels out to be X. You'll notice that the ATMs cancel out and we're left over with liters. So 32.77 divided by 1.21 comes out to be 27.08 liters. We want three significant figures because every one of those numbers have three sig figs. So it's going to be 27.1 liters. The next example. A balloon is put in a bell jar and the pressure is reduced from 782 torr to 0.500 atmospheres. So P1, V1, P2, V2. Our first pressure is 782 torr. Our second pressure is 0.500 atmospheres. Those are both units of pressure, but we need them to be the same unit. So I'm going to divide the torr by 760 because there's 760 torr in 1 atmosphere. That comes out to be 1.03 ATMs. If the volume of the balloon is now 2.78 times 10 to the third milliliters, what was it originally? So the first thing we want to do is set up our equation. 1.03 ATM times X is equal to 0.500 ATM times 2.78 times 10 to the third milliliters. We're going to multiply that out. So 0.5 times 2.78, that equals 1,390 ATM milliliters. 1.03 ATM times X. X is now equal to 1,350 milliliters. We need three significant figures. So 1.35 times 10 to the third milliliters. Charles's law. Charles's law relates volume and temperature to one another. They're directly proportional. This time the pressure stays constant and the amount of a gas stays constant. Remember, the amount of a gas is moles. Graph of the volume versus temperature turns out to be a straight line altogether. So as temperature increases, so does the volume. Unlike previously, where we said that as long as the volume's matched up and the pressure's matched up, the temperature has to be in Kelvin. That's really important. So this equation is really important. We always have to make sure it's in Kelvin. If it's not, if it's in Celsius, we have to add 273. So the volume is equal to a constant times temperature because the volume and temperature divided by each other is a constant. If we look here, here's the same compound. These are all oxygen. As the temperature increased, so did the volume, and it created a straight line in the process. So let's look at Charles' law from a molecular point of view. The pressure of a gas inside and outside the balloon is theoretically the same. As the temperature decreases, the molecules inside slow down. Therefore, hit the sides of the balloon softer, therefore the volume gets smaller. So let's take a look at an example problem. Those are the units I need. 2.57 liters at 0.00 degrees Celsius. I know I need to have this in Kelvin, so I'm going to go ahead and add 273 right now, so I don't have to do it later. What is the temperature at 2.80 liters? Alright, so V1 is 2.57, T1 is 273, V2 is 2.80, and T2 is what we're looking for. First thing we're going to do is cross multiply. So that's 2.57 liters times X is equal to 764.4 Kelvin times liters by multiplying these two together. Divide both sides by 2.57. The liters cancel, and that leaves us with 297 Kelvin. Let's try another one of those. The temperature inside the balloon is raised from 25 degrees Celsius to 250 degrees Celsius. If the volume of the cold air was 10 liters, what's the volume of the hot air? So V1, T1, V2, T2. The first volume is 10.0 liters. It's going from 25 degrees Celsius. We're going to add 273 to this to make it to Kelvin. That's 298. We want to know what the second volume is, and it goes up to 250 degrees Celsius. We're going to add 273 to that as well to be 523. Alright, so let's put our numbers in. 10.0 liters over 298 Kelvin is equal to X over 523 Kelvin. Cross multiply 5230 liters dot kelvins is equal to 298 kelvins times X. Divide both sides by 298. And that comes out to be 17.6 liters is X. Finally, we have Avogadro's law. You might remember his name before by talking about the Avogadro's number was 6.022 times 10 to the 23rd, and he came up with the concept of moles. So his relationship is dealing with moles, which is what the N is. The volume is directly proportional to the number of gas molecules, while the pressure and temperature are constant. More gas molecules means that there's going to be more volume. Count the number of gas molecules by the moles, which is what the N is, and equal volumes of gases contain equal number of molecules. The actual gas doesn't matter. Alright, so this equation is V1 over N1 is equal to V2 over N2. So 0.225 moles of sample of helium. So that's going to be our N. Has a volume of 4.65 liters. How many moles must be added to give 6.48 liters? Alright, so V1 is 4.65 liters. N1 is 0.225 moles. 6.48 liters over X. Cross multiply. That comes out to be 1.458 liters times moles is equal to 4.65 liters times X. Divide both sides by 4.65. Those cancel. And that comes out to be 0.314 moles. That's how many the total moles would be. If you need to know how many you needed to add, it would be 0.314 moles minus 0.225 moles. That's how much would actually be added. And we're going to have one last example. If 1 mole of a gas occupies 22.4 liters at STP, what would the volume be at 0.75 moles? So V1, N1, V2, N2. V1 is 22.4. N1 is 1.00 moles. We're looking for the second volume at 0.750 moles. 22.4 over 1.00 moles is equal to X over 0.750 moles. Cross multiply. That comes out to be 16.8 liters times moles. 1.00 moles times X. Divide both sides by 1.00 moles. And we get rid of that unit moles. So we have 16.8 liters is equal to X. That gives you an explanation of the 3 gas laws.